Salam and welcome everyone. So today we're going to be working on the question on the screen that says calculate the energy of the quantum involved in the excitation of an electronic oscillation of period 2.50 fs. Then number 2, a molecular vibration of period 2.21 fs, and number 3, a balance wheel of period 1.0 ms. So by the way, this FS and then MS is just telling you that you're dealing with here 2.5 times 10 to the power of negative 15 seconds. It's just how you have kilo, which is just times 10 to the power of 3. You have a micro, which is times 10 to the power of negative 6, right? Centi times 10 to the power of negative 2. So all of this is just basically what this FS stands for. Its S is still seconds. So in this case, 2.21 fs is just 2.21 times 10 raised to the power negative 15 seconds. And then 1.0 ms, that's milliseconds, so times 10 raised to the power negative 3 seconds. So I just wanted to make sure everybody understood that for now. Then they say express the results in joules and kilojoule per mole. Now, another thing you also have to know is the fact that number one, number two, and number three are three independent questions, and they are not questions that rely on each other. So for example, I'm not gonna solve for number one and use the answer in number one to solve for number two. Neither am I going to solve number two and use the answer to solve for number three. Your three independent questions were just asked to calculate the energy of the quantum of each one of the three questions. So the first thing you have to do now that we have all of this information clear is for us to write out the energy. So the energy of quantum is just simply equal to h times frequency, where h is equal to the Planck's constant, which is just 6.626 times 10 raised to the power of negative 34 joule seconds. And then the frequency was not given to us. And yeah, we don't have the frequency, so we need to calculate whatever the frequency is in order for us to be able to determine what the energy of quantum is. But before we go ahead, we have to remember, because a lot of these advanced chemistry courses or science courses, they build on fundamental knowledge. So for example, now remember in physics, you were taught periods, as well as frequency and pendulums and vibrations and things like that. Just remember that when you're dealing with period, you're dealing with a value or a parameter that has the unit of seconds. But you can also determine what a period is by knowledge of the frequency. For example, now we know frequency is how many cycles that is going to take per second, and then the period is how many seconds is it going to take to complete a full cycle. So therefore, the formula that connects period and frequency is equal to 1 over t. So they are basically inversely proportional, or you can have the period itself is equal to 1 over v. So frequency is equal to 1 over period, and period is equal to 1 over frequency. Now, with this knowledge and the fact that we know that we've been given the period's value, we can determine frequency. So now let's of course note this. The change in E that was equal to H times V can now be written as change in E, okay, is equal to H divided by T, where we substituted the value of V to equal 1 over T. So yeah, that's it. So this is the formula we're going to use. Now the first question says an electronic oscillation of period 2.50 fs. So the first question, 2.50 fs, 2.50 times 10 raised to the power of negative 15 seconds is going to be the value for t. So we just simply, to calculate the energy of quantum, which is what the question requires, is that you write this here. You just have 6.626 times 10 raised to the power of negative 34 joule seconds divided by the period, which is just 2.50 times 10 raised to the power of negative 15 seconds. So you cancel out the seconds, and then what you end up with is change in E is equal to 6.26 times 10 raised to the power of negative 34 joules divided by 2.5 times 10 raised to the power of negative 15. The answer ends up becoming 2.6504 times 10 raised to the power of negative 19 joules. So this is basically it. Now, You'll be wondering, okay, yeah, this is pretty straightforward. We've gotten the right answer, which is actually true. We've gotten the right answer, but our work is still not done because we have to make sure we put the work in the proper number of significant figures. So changing E, okay, is actually going to be in three sig figs, because the first question we're giving 2.50 is actually in three sig figs, so we have to put our final answer in three sig figs. So that would just simply be 2.65 times 10 raised to the power of negative 19 joules. And this is the answer to this first question. This is the energy of the quantum. Now, we're going to go back to the question because I just realized something and I want you guys to take note of this. You can see that while they asked us to calculate the energy of the quantum wave the excitation of three independent questions below of different periods, we're also told at the very end to express the results in joules, okay, which we've successfully done, and in kilojoules per mole. So I want to explain this, and there are other videos that have this explanation as well, and I'm going to do the same thing in this video. So in order for us to be able to solve in terms of kilojoule per mole, we have to note that what this is just telling us is that we're going to have our energy, and the energy is going to be, we're going to basically find molar energy per mole. How you know you have molar heat capacity, where it's just the heat capacity divided by the number of moles, or you have a situation where you're dealing with molar volume, the volume divided by moles. So that's basically what we are asked to do here. But now I have to quickly mention something to you. The energy per mole, the formula for it is very, very straightforward, and you have to also use your fundamental knowledge of science to be able to do it. So we don't know the energy per mole, but we know that we want our final answer for energy per mole to be in kilojoule per mole. Now, you'll be wondering, well, they didn't give us the number of moles of the quantum. And you're going to be wondering, how do we do a question like this? Well, the way you do a question like this is to go back to your fundamental knowledge of chemistry. So go to the fundamental knowledge of chemistry, where we know that 1 mole, okay, I'm taking you back to the basics, 1 mole of an atom, molecule, ion, and any other form of particle or any other form of quantity like a substance, a sample, is always going to give you the Avogadro's number. You have to always know this. It's always going to give you the Avogadro's number. So basically, 1 mole of anything is going to equal 6.022 times 10 to the power of 23 particles. So basically, what they're trying to say, if 1 mole is always going to give you this, the unit for Avogadro's number is just 6.022 times 10 to the power of 23 per mole. So basically divided by mole. So this is basically the Avogadro's number, and the unit for it is 1 over mole, or mole raised to the power of negative 1. So I just wanted to mention this to you, and it makes sense because you already know that 1 mole will give you this quantity, 6.022 times 10 to the power of 23. Now, what you're going to do now is use this knowledge I have just said to derive the formula we're going to use for energy per mole. So energy per mole is just simply the energy of the quantum change in E that we solve for times the Avogadro's number. So yeah, that's it. That's just basically how you have to do it. We see that we have our change in E, which is the energy of quantum, to be 2.6504 times 10 to the power of negative 19 joules. So we can just say E mole here is just going to be 6. Wait, was it 6 I just said? 2.6, sorry, 504. 2.6504 times 10 raised to the power of negative 19 joules, okay, times number of moles, which is just 6.022 times 10 raised to the power of 23 per mole. So that's basically this one right here. So when you have this, E mole is going to equal 1.590607 times 10 raised to the power of 5 joule per mole. So this is basically the answer to this question. Now, I just wanted to quickly mention something to you, that because of we've gotten our final answer, does not necessarily mean this is how it's supposed to be. we have to put our work in the proper number of significant figures. And when we go back to the question, we see that 2.50, the original question, was given to us in three sig figs. So we have to maintain that because we also use the values one way or the other to solve for the energy per mole. So this is just simply going to be in this case here. So that would be energy per mole is equal to 1 point. The when you round this up, you're just going to end up with 1.60 times 10 raised to the power 5 joule per mole. But also, let's not forget this, right? We already know that the question asks us to solve our question in kilojoule per mole. So we have to go from joules to kilojoule per mole. That's just basically dividing by 1000. So the energy per mole is simply going to be 1.60 times 10 raised to the power of 2 kilojoule per mole. And that is basically the answer to this question. So we have successfully determined the energy of quantum, and we've also successfully determined the energy of quantum in kilojoules per mole. So yeah, that's basically how you answer. Now, I know I went through a lot of detail at the beginning. Now we're going to do the second and third, and we're just going to solve it as a way of practice. Yeah, so that's it. So the second question is 2.21 Fs or 2.21 times 10 raised to the power of negative 15 seconds, which is just simply the period. And remember, when we rewrote the formula, we saw that the energy of quantum is equal to hv or h divided by t, where t is the period and v is the frequency. So change in E is equals to this one here. So we have the Planck's constant 6.6. This is the Planck's constant, by the way. I know I've talked about it before, but I want to make sure that everybody's on the same page as much as possible. And then this is your period. So Planck's constant H, that's 6.626 times 10 raised to the power of negative 34 joule seconds divided by 2.21 times 10 raised to the power of negative 15 seconds. Changing E is equal to 6.626 times 10 to the power of negative 34 joule seconds divided by 2.21 times 10 to the power of negative 15 seconds. So when you just do the calculations, you end up with a situation where you get 2.998192 times 10 raised to the power of negative 19 joule. And I want to quickly mention something. I forgot to cancel out the units. So you cancel out the seconds here, you cancel out the seconds. So that's the reason why your final answer is in joules. So yeah, this is basically our answer. We have successfully solved for this to get the energy of quantum with period 2.21 times 10 to the power of negative 15 seconds to be this energy we just solved for. And we already know the proper thing we're supposed to do in chemistry is to put in the proper number of sig figs. And we have a question where we're supposed to put the final answer in three sig figs, right? 2.21 is three sig figs, so the final answer has to be in three sig figs. So change in E ends up becoming 3.00 times 10 raised to the power of negative 19 joules. So this is basically the answer to this question. So we've done the first part. We have expressed our answer in joules. Now we have to do it in what? Kilojoule per mole. So E mole is equal to changing E times Avogadro's number. Yeah. So we already know change E mole is just going to be changing E. We know that to be 2.998192 times 10 to the power of negative 19 joules multiplied by the Avogadro's number 6.022 times 10 to the power of 23 divided by mole, because that's the units for Avogadro's number, 1 over mole, or mole raised to the power of negative 1. I wanted to quickly mention something. Some of you may be wondering that I did the exact same thing I did in the previous question here, where whenever we are asked to substitute or whenever we're solving for emo, I'm substituting the raw value rather than the approximated value. Whenever you're doing questions like this in science, as far as you've not gotten the final answer to something and you're going to be using an answer that you already solved for, you have to use the raw values because you want to make sure that the new calculation you're doing is as accurate and as correct as possible. So we do not use the rounded number to do further calculations. We only use raw values to do further calculations. So I'm sure some of your professors would have told you that, but it will be surprising to hear Some of you may be wondering why am I saying this, but they're actually students that do not know that you're not supposed to do that. So anyways, 2.998192 times 10 to the power of negative 19 times 6.022 times 10 to the power of 23 is just going to give you 1.80555112 times 10 raised to the power of 5 joule per mole. So again, we already know our work is going to be in three sig figs. Sorry, our final answer is going to be in three sig figs. So you have that here. So emo is just simply going to equal 1.81 times 10 raised to the power of 5 joule per mole. Now, I wanted to quickly mention something. You see, now that we've done this, the question still says we should solve in kilojoule per mole. So our answer, when we convert from um this answer here from joule per mole to kilojoule per mole, we're just going to divide by 1000. So we end up with E mole is going to equal 1.81 times 10 raised to the power of 2 kilojoule per mole. So that is basically the answer to this question. Successfully, we've done it. We've really, really, really done it. Yay! That's all. So the third question is this question right here. 1.0 ms. So it's just 1.0 times 10 raised to the power of negative 3 seconds. So we already know that's what our period is. So that's T. We know the formula we're using is the energy of quantum changing is equal to Planck's constant divided by period. So we just simply substitute Planck's constant. We know that to be 6.626 times 10 raised to the power of negative 34 joule seconds divided by the period 1.0 times 10 raised to the power of negative 3 seconds. We cancel out the seconds. And then, of course, changing E will be this information we put in our calculator. When we do the calculation, we end up with 6.626 times 10 raised to the power of negative 31 joules. Now, of course, we're going to put this new answer that we solved for in proper number of significant figures. And we see that 1.0 is two sig figs. So we have to put our work in two sig figs. So changing E ends up becoming 6.6 times 10 raised to the power of negative 31 joules. And this is basically the answer to this question. So even though we've successfully done this, remember the question is also asking us to express our answer in kilojoule per mole. And to do that, we're going to use Avogadro's number. So E mole is changing E multiplied by Avogadro's number. So the energy of quantum multiplied by Avogadro's number. So E mole is going to equal 6.626 times 10 to the power of negative 31 joules. Again, we're using the raw values, not the approximated value. Times 6.022 times 10 raised to the power of 23 per mole. So yeah, that's it. So E mole is going to be 6.626 times 10 to the power of negative 31 times 6.022 times 10 to the power of 23 per mole will end up being 3.99 018 times 10 raised to the power of negative 7 joule per mole. Now again, we already know we've got to approximate, right, in the proper number of sig figs. And we see that in this question, we're dealing with a two sig figs initial question 1.0 ms. So we're just going to do this and round up to two sig figs. And when we do that, we end up with E mole is equal to 4.0 times 10 to the power of negative 7 joule per mole. And remember as well that we're not supposed to leave our final answer in joule per mole, but in kilojoule per mole. So we're going to divide this information here by 1000 to get kilo. So E mole ends up becoming 4.0 times 10 raised to the power of negative 10 kilojoule per mole. And this is basically the final answer to this question. So if you have any questions, suggestions, concerns regarding this video or the channel, make sure you put it in the comment section. If you're confused about what I've done, please rewatch this video at a slower speed. And there's also a similar question on my channel that is going to be linked in the description so that you can learn more about this particular topic or style of question. If you need help in any of your STEM related courses, whether you're in middle school, high school, or college, I am the tutor for you. I help my students succeed in all their STEM related courses as well as improve generally in academia. So if you would want my services by the way of tutoring and mentorship, please try to email me at yourhappytutoring@gmail.com. I look forward to working with all of you and helping you on your success journey. I wish you guys all the very best. Assalamu alaikum wa rahmatullahi wa barakatuh.